Okay, so so from any eigenvector of B, we can get an eigenvector of A. So again, like I mentioned before, from you have m eigenvectors of B will lift to m eigenvectors of A. I mean, there's one thing we actually didn't mention is that this PV, in order to be a bona fide eigenvector, it has to be non-zero. But you see it the way PV looks like. It's you get V1 on the positions indexed by x1, V2 on the positions indexed by x2, and so on. And because V was non-zero, at least one of these V1, V2, Vm is non-zero, and that implies that PV is non-zero. And actually, the other thing is that if you have these eigenvectors of B, which are linearly independent, you will get, the corresponding eigenvectors PV will also be linearly independent, and you'll get m eigenvectors of A this way. Okay. Now, for the second part, so what did we say about the second part? That we can get, so we'll get eigenvectors that are constant on the sets x1, x2, xm, and then we'll get these eigenvectors that are, how to say, they're perpendicular, so they sum up to 0 on those parts. So there's a bit of subtlety here involving, again, linear algebra. So the equation, this key equation, AP equals PB, it's actually the same thing, I write it here, as the column space of B, which I denote by called P, is A invariant. Okay. So there are a few things there. So call P is the column space of P, and it's the subspace of Rn spanned by the columns of P. Okay. Now, like I mentioned before, the key observation here is that when I look at P, I see P as this, let me call its column C1, C2, Cm. Okay. So if I multiply this by a vector x1, xm, then the result is x1 times column 1 plus xm times column m. So any vector in the column space looks like this on the right. So essentially, the column space, what I'm saying is that the column space of P looks like vectors of this form, P times x1, xm, where x1, xm are real numbers. Okay, so column space of a matrix P is everything of the form P times admissible vector. And the same thing happens on the other side with the row space, but you multiply to the left. Okay. Now, what do we see when we look at this equation? Okay, so this takes care of the column space. I need to tell you what this call space of P is a subspace. So it's a subspace of Rn. Now, what does it mean that if we have, let's say in general, a W, a subspace of Rn, what does it mean that this is A invariant? This means that if for any W in W, a W stays in W. Okay, that's what it means. And now, so the equation, so AP equals PB, implies that any, essentially what we're doing on the left-hand side. So on the left-hand side, we're multiplying each column of P gets multiplied by matrix A, okay? So it's A is multiplied by each column of P. And now, what is the result? The result is B times P, and this B times P, the columns here, the columns in this matrix, P times B, which is again a tall matrix, these columns are linear combinations of the columns of P. So basically, we take any column of, on the left, we take any column of P, we multiply by A, and how does the result look like? Well, it looks like linear combinations of columns of P. So it's exactly, this implies that the column space of P is A invariant. Okay, it's actually equivalent. That's how you write that the column space of P is A invariant. Okay. And now, okay, but now from linear algebra, so what do we care about these A invariant subspaces? Well, that's what eigenvectors are, and eigenspaces are. So what we can say from linear algebra is that because the column space of P is A invariant, I won't prove this here, but I'll put it in some notes on the Google Drive. This implies that column space of P has a basis formed by eigenvectors of A. Now, if you look at the column space of P, so this column space is spanned by the characteristic vectors of these subsets x1, x2, all the way xm. So I just pick up each column individually. And how do these characteristic vectors look like? Well, for x1, it has a 1 on the positions corresponding to x1, and it has a 0 everywhere else. x2 is similar. It has a 1 on the positions corresponding to x2 and 0 everywhere else. And the last one, xm, has 1 on xm and 0 everywhere else. So if you take linear combinations of these vectors on the positions that correspond to vertices in x1, you will see the same value. So and on the positions indexed by the vertices in x2, you'll see the same value, and so on. So basically any vector in the column space of P, of this matrix P, is constant on these subsets of the partition. So that means that the eigenvectors of A that span the column space of P are of the form PV, are the ones that we just PV, and are constant on the subsets x1, x2, x3. Okay, so this is just a reformulation of, in some sense, of part 1. But now here comes again a fact from linear algebra. Because the column, you have a subspace that is A invariant, like column space of P is A invariant, that implies that its orthogonal complement is also A invariant. So I'll leave this as an exercise. And so, okay, but what does that mean? By the same argument that we have earlier, we can find there is a basis call the orthogonal formed by eigenvectors of A. So these eigenvectors of A have to be perpendicular. So these eigenvectors of A are orthogonal on each column of P, and therefore, if you're orthogonal, let's say on the first column, the column corresponding to x1, if you're orthogonal to it, it means that you sum up, when you do the dot product, it means that the sum of the entries on x1 are 0. So they each of them, let's say each such eigenvector sums up to 0 on every subset x1, x2, xn. Okay. And now this can be rephrased in the following way that may be useful in some situations, is that these eigenvectors are eigenvectors of the matrix A prime, which is obtained from A by changing the, let's say, ij block. I'll explain in a second what this is. Aij to Aij plus some const Cij times the all one matrix Cij. So what do I mean here is that the original matrix A, if you think of it as this big matrix, its vertices can be partitioned according to, okay, so it's a square matrix, and its vertices can be partitioned to, you have x1 there, x1 on the top, and maybe you have x2. So I mean, in general, they don't have to be consecutive, but for simplicity, let's just think of it that way. And let's say xm at the end, xm here. Okay. And now what does this do is that it breaks the matrix in these blocks corresponding to these partitions. So if I have somewhere here some xi, and if I have somewhere on the top some xj, the place where they meet, like if you draw this block matrix this way, and this one comes down here this way, that's what we have this matrix. This is what we mean by Aij. So this Aij is essentially cardinality of xi by cardinality of xj sub matrix of A. Okay. And because these these vectors, the second type of vectors that we have, are perpendicular on all these characteristic vectors, it's not too difficult to see that they will be eigenvectors of A, but because when you multiply them by all one matrix of a right order, they give you 0, then you can replace, they will be also eigenvectors of a matrix obtained from A by replacing this Aij, changing this Aij by Aij plus any multiple of the all one matrix Jij. So we can put Cij, Jij. So that's what is meant here. Okay, so let's do an example and see how this works out, and we can go from there. So here's a graph. So let's say we take we take a complete graph on A vertices here. And over here, we take K disjoint edges. So this one, let's just take it K times K2 in the blue. And what we do this operation of what is called a join. We put all the edges in between. So we put here all the edges. Okay. Now, in a particular example, we've seen this already. So for example, when A equals 1 and K equals 3, the graph on the top is just a single vertex, and you have 3 edges here, and they're joined this way, this way, this way. And this is one of the examples of a graph in the previous class. In general, when A equals 1, this graph is called the friendship graph. Friendship. I mean, let's just call it FK, and it consists of it's basically K triangles sharing a vertex. So in our situation, you have that, but you can have, more. And we'll prove this in one of our future lectures, that the friendship graphs are the only graphs with the property such that the any two vertices have exactly one common neighbor. So this is a classical result in graph theory. I think it was proved independently by Erdos, Kovarian, Schoch, and Wilf, if I am not mistaken. And so you can think of a graph representing some kind of social network, friendship network, and so on. And you can ask this question is, okay, which network are the ones in which every 2 people have exactly one common friend? And it turns out that these are the only graphs. And it's easy to see why that's true in these graphs, because if you take any 2 vertices, if you take the center and any other vertex, there's a unique triangle that contains them. And if you take any 2 vertices on the outside, they're both connected to the center. But it's a bit harder to prove that this is the only these are the only graphs with this property. And we'll give a proof in one of our coming lectures, and it uses also eigenvectors and eigenvectors, so linear algebra. But anyway, so this is a friendship graph. So coming back to our problem, we have this graph Ka. So maybe for simplicity, let's just do the friendship graph instead of Ka. So we have, let's just do the one with A equals 1. So we have this graph all the way like this. It has K, K2. What are the eigenvalues? What are the eigenvectors? So we discussed it before. You can find an equitable partition fairly easily. You can divide them into the vertex on the top, it's x1, and the vertex is here, this is x2. And if you check the condition of equitable partition, you will see that it's satisfied. And we get a quotient matrix if we label the vertices in this order, so x1 first and x2 second. So the vertex on the top is adjacent to how many vertices in its own set? It's adjacent to 0, but it's adjacent to 2k vertices across. And if you pick any vertex in x2, it's adjacent to exactly one vertex in x1, and it's adjacent to exactly one vertex in x2. So this is a quotient matrix. And when you do the calculations, you will get two eigenvalues from here. So let's just quickly do the characteristic polynomial of this matrix. So phi b of x, determinant of xi2 minus b, and is what? X times x minus 1 minus 2k, and we get x squared minus x minus 2k. What do we get? The discriminant is 1 plus 8k, and we will get two eigenvalues. Let me write them in red. Theta 1, theta 2, b1 plus or minus square root of 1 plus 8k divided by 2. If you want to kind of ballpark them a little bit, you can look at the theta 1 is 1 plus square root of 1 plus 8k over 2. How large is this? Well, just ignore the 1 from the square root. You get about 2 square root of 2 times square root of 2k. So it's about square root of 2k, the top one. And this one is 1 minus 1 plus 8k over 2. Roughly speaking, it's about minus that much. So you get one positive and one negative. Now the question is, okay, so this graph, so here we have 2k plus 1 vertices. So we found two eigenvalues. We have how many left? They're like 2k minus 1 other eigenvalues. What are they? How can you find them? Okay. Now we go back to the theory. So these eigenvalues, theta 1 and theta 2, they're eigenvalues of the quotient matrix. So their eigenvectors are the ones that are constant on the sides of the partitions. Okay. So these are the ones of the first type, the ones that we get immediately from B. Now for the other ones, we look here in this situation, we're looking for eigenvalues whose eigenvectors are perpendicular to the sets to x1, to the characteristic vectors of x1, x2, xn. Okay. Okay. Now, if you're perpendicular on those characteristic vectors, so let's do x1 here, and let's just do it. Okay, one. Okay, in this situation where you have this way. So that's x1 on the top, and the x2 is the one at the bottom. Let me do different colors. So this is x1, and this is x2. So if you are perpendicular on the characteristic vector of x1, so I will do now, I will label the vertices with the eigenvector entry. It means that your eigenvector entry there is 0. Okay. And now we will think about how can we label these vertices at the bottom such that we get this property that the sum, you want that for each vertex, the sum on the of the eigenvector entry on the neighbors of that vertex equals a multiple of the entry in that vertex. So let me show you one way that this can be done. So you can do, so you have 0 on the top, and you can do 1, 1, minus 1, minus 1, and then you can put 0 everywhere else. Okay. And if you label them this way, what do we get? Then the eigenvector that the eigenvalue that we'll get this way, will be an eigenvalue of 1 corresponding to this eigenvector, because on the top the equation is satisfied because you have 1 times 0 equals the sum on the neighbors, but the neighbors are 2 of them have 1 and 2 of them have -1, so that cancels out. The equation is satisfied wherever you have all zeros, so you only have to check it in these triangles that have 2 1s or 2 -1s, and you will see that is satisfied. If I am here, for example, at this vertex, the sum of the eigenvector entries on the neighbors is 0 plus 1, which is 1, which is eigenvalue 1 times 1. So if you do that, then you can actually get a bunch of eigenvectors by this argument. And let me show you how you can get more. So let me draw a bigger picture here. So you can do the same trick, 0 here. You can put a 1 1, you 0 0, and you move the -1 to the -1 here, and you go all the way this way. This is also an eigenvector for eigenvalue 1, but it's linearly independent from the first one because one has non-zero entries where the other one has zeros entries. So by repeating this argument, moving this -1 all the way to the right, you can get, so this one is an eigenvector. So by repeating this procedure, you can get k minus 1 linearly independent eigenvectors corresponding to the eigenvalue 1. Okay, so we got k minus 1. Well, so let me find the other one and then we'll be done. So we have 2, we have k minus 1 ones. Where are the others? Just before you put a 0 on the top. So in this situation, we did 1 1 minus 1 and so on. Here you can do 1 minus 1 and you can do 0 0 0 0 0 this way. And in this situation, if you do the calculation, this corresponds to eigenvalue -1, and you can move this 1 and -1 around, and again you get some eigenvectors that are linearly independent. So you put 0 0 here, you put the 1 -1 here, 0 0 0, and you go all the way to the end. This one here at the end, you'll get 0 0 0 0 0 0 and 1 -1. And by the same argument as before, like I said, you can show that these are linearly independent, and so there are k linearly independent eigenvectors for 4 -1. So if you want to do the spectrum of this graph, this is the whole spectrum. So we have 1 plus square root of 1 plus 8k. It had multiplicity 1 over 2. I'm sorry. And then we had the eigenvalue 1. So I'll write them in decreasing order. 1 has multiplicity k minus 1. -1 has multiplicity k. And the other one is 1 minus square root of 1 plus 8k over 2 has multiplicity 1. And that's it. All right, so I'll stop here.